So as I said that we have discussed about addition and subtraction in chapter number 4. That means we have discussed about add instruction, increasing instruction for the addition, and subtraction for subtraction, and also the decrease one. Now we are going to discuss about fourth instruction regarding multiplication and division. MUL for unsigned number multiplication, and IUMUL, which is the integer multiplication, right? Which is for multiplication. For division, same division for unsigned number, and I division for signed number. So let's start with the multiplication instruction. So in this multiplication instruction, right, we have little bit of complicated compared to the addition and subtraction. So they define, or they find out two issues. Issue number one is whenever we do addition and subtraction, if you add two 8-bit number, so the result will be maximum 8-bit number with one carry bit maximum, right? Subtraction, if you subtract from 8-bit minus 8-bit, obviously the result will be 8-bit long. But in multiplication, it's not like that. In multiplication, if you add 8-bit multiplied by another 8-bit data, the result will be 16-bit long. That means double. You cannot store an 8-bit multiplied by 8-bit result into an 8-bit position, because we need more, because it is doing multiplication. So that means the ground rule is, if you multiply by 2n bit of variable or value, your result should be stored into the 2n bit type result. That means if it is 8-bit multiplied by 8-bit, you have to have a storage which is 16-bit long. If you multiply 16 multiplied by 16 another value, it should be, you should store that result into the 32-bit storage. All right, same as 32 multiplied by 32, you have to store into the 64-bit of storage, right? So that is the issue number one. Issue number two is signed or unsigned. Previously in addition and subtraction, we don't bother about it, either it's a signed number or it's an unsigned number. But here we have a little bit problem. Okay, let's see the two example. So look at this example, example number one, where we are multiplying 8-bit with another 8-bit value. All right. So here 8 bits are all ones. All one means this is an unsigned number. So all one means 255 in decimal number. So we can easily understand that this is 25 multiplied by 25, 255. Sorry. Okay. So result is this in binary. So we assume that this is unsigned number, and this is all one. All one is 255, and all one is 255. So the result is this. But if you think same bit pattern, similar 11111, if you think that this is signed number, right? If this is a signed number, this all one does not mean 255 in decimal number. If you think this is a signed number, it will represent actually -1. Okay, I hope I have shown you how it is -1. We know that if you want to convert from positive to negative number, we have to make that value in the bit in the 8-bit, 16-bit, or 32-bit number. So in this case, our value is 1. So let's say this is 1. So this is 1 bit. So we need to convert it into the 8-bit number. So we just add 70 before it. So now it is 8-bit number. So after having the 8-bit number, we need to take its 2's complement of this number. That means convert them 1 to 0, 0 to 1, and then plus 1, and then we have our 2's complement. And this is actually the negative number of this number. So that's why we can see that all 1 in 8th position, if it is 1, we can consider it as -1 if you think that is a signed number. That's why similar types of bit pattern, previously all 1 means 255 because it's an unsigned number. But if you think it's a signed number, all 1 in 8th position means -1, not 255. So this is -1, and that is again -1. So -1 multiplied by -1 is +1. That is the result. I hope you can understand the problem that similar types of bit pattern, all 1, all 1, all 1. But If it is unsigned, the result is this very big number because it's 255 multiplied by 255. But if it is a signed number, the result it is just this 1. Alright, so that is the difference between if you think it's a signed or unsigned number. Okay, so we need to consider these issues whenever we are going to multiply. Whenever we are going to multiply, we need to consider these two issues, that 8-bit multiplied by 8-bit should have 16-bit result, and we should consider either it's a signed number or unsigned number. Okay, so let's try for the signed number first. So if it is a signed number, the code is this MUL source. Source means any either it's a register or any other memory location. In this case, we are using a register. Okay, so MUL multiplication and then source. That is the equation. That is the instruction for unsigned number, not signed number. So the question is, we have two numbers to multiply, this one and that one. So we have only one. Where is the other one? So the other one is depends on the size of the source. We assume that the other number, that means this number, will be stored into other register location. Okay, and this multiplication can be done in 8-bit, 16-bit, and 32-bit. These three types of multiplication by this instruction. Okay, so let's one more thing, that immediate specific is not actually allowed. So that means you cannot write this. It must be a memory location. All right. So let's see these three types of multiplication. First type is if the source, if the source is 8-bit long, the assembler assume that the other variable, that means the other operand to multiply, is actually stored into the AL register, because AL register is an 8-bit register in data register, in the first register, EAX. This is the lower part, right? So they assume that this is one source we are giving, but another source is still stored into the AL register. Then we multiply this 8-bit multiplied by 8-bit, and then the result, we know that the result will be 16-bit long, right? So the lower part of the 16-bit will be stored into the AL register, same, and then the higher part will be stored into the AH register. Okay, because our result, we assume that it should be 16-bit long because it's 8-bit multiplied by 8-bit. So let's see what about the 16-bit source. So if the source is 16-bit, right, we assume that other operands is stored in AX register, which is 16-bit long in the data register Pentium processor, if you can remember. So if you multiply 16, we must have a 32-bit storage. So the lower part of the multiplication result should be into the AX register, right? And higher part will be stored into the DX register. Please remember these two, AX and DX, and these are same. Look, these are same. Okay, the operands we have stored here, we store the result in the lower part of the result into the operands after the multiplication. Very similar to if you write C equal to C plus 1, right? Similar, because C is the value, C has a value, you add with plus 1, and then after the addition you store the value into the C again. Same result here. Okay, so let's see what about the 32-bit source. Okay, 32-bit source. So if your source of multiplication is 32-bit, the assembler assume that the other operands will be stored into the EAX register. I hope you know what is the EAX register. It is the first register in our data register Pentium processor accumulator, EAX. Okay, so to this multiplication we are actually using two registers. One is EAX, another one is EDX. EDX is data register, EAX is our accumulator register. Both of them are using for this kind of multiplication and division. Okay, so if it is 32-bit multiplied by 32-bit another number, so the result should be stored into 64-bit location, but we don't have any 64-bit register. So what we do, lower part of that 64-bit will be stored into EAX, into 30-bit register, and the higher part will be into EDX. Okay, so that's how we do the multiplication of 8-bit, 16-bit, and 32-bit. If you just compare these three procedure, there are so many similarities. What are the similarities is, we have the source, but other operands will be stored into one register, and after the multiplication, the lower part of the answer will be stored into the operands. That's why this column and that column are same. Look, AL AL, AX AX, EAX EAX, right? That means wherever your other operands is stored before the multiplication, after the multiplication, the lower part of the result will be stored there, and the higher part of the result will be stored into other register. In this first case, it is AH because both of them combinedly make AX register, right? If it is 16-bit, you have AX and DX. For 32-bit, same. Instead of AX, we have EAX. Instead of DX, we have EDX. These two also similar. AX, EAX. DX, EDX. AX, EAX. Okay, so there are similarities. So if you understand one, I hope you can understand the other one also. All right, so that is the way we can do the multiplication. Fine. So there is also a little bit other things also. Let us show you two more example. I hope if you understand this example, this multiplication is super easy. All right. So what are the example? What are the two things? Is we need to consider for this multiplication, we need to consider two flags, two status flag actually. These are two status flag, by the way, carry and overflow. Carry and overflow. By the way, this status flag will just give you the status. It's not an error message. Okay, it just tell you the microprocessor that what type of data we have. Either it's a carry or overflow, or both of them. Okay, so let's see how. For example, look at this example very clearly, closely. What is it? We are moving a value of decimal number. By the way, these are decimal number. So we are converting decimal number. Not we are moving the decimal number 10 into AL register because it's 8-bit. We are moving 25, value of 25 into DL register. That is another 8-bit. All right. And after that, we are going to do MUL That means this is whenever you write MUL a register or a source, that means this is an unsigned multiplication. If you write MUL, that means it's unsigned, signed multiplication. But you are writing MUL, that means it is unsigned. So we don't worry about the sign. Okay. So let's multiply. So if you multiply 10 multiplied by 25, what will be the result? 250, right? 250. So according to the rule, this is 8-bit. Remember, this is 8-bit. So according to the rule of 8-bit, we are going to store the lower part of the result of 250. If you convert into the binary, the lower part will be stored into the AL register, and the higher part will be stored into the AH register. Fine. And both of them are 8-bit. But the question is, we have 8-bit register in AL and we have 8-bit. If you have 8-bit, listen carefully, if you have 8-bit, what is the maximum number you can store into a 8-bit register in a decimal number? You have 8 bits, okay, 100 like that. What will be the maximum number you can store in an 8-bit decimal number? 255, right? 255. I hope you understand, because if it is let's say for example this is an 8-bit position. So if it is 8-bit 111111, that is the maximum number you can store, right? This is what is the equivalent of this? This is actually 255. This is the decimal number. That means you maximum can store 255, the value of 255 into an 8-bit position, right? I'm sorry. So that's why how much, so in AL register, what is the maximum number you can store here? 255, right? Do you understand?
Yes, sir.
So you can store into this register 255 maximum, but after the multiplication, what is our result is 250, right? 250. So we can easily store the 250 into the AL register, right?
Yes, sir.
Yes. That means, do we need to have any overflow of this here? Do we need any extra bit from the higher order? Because AL register can store 250, right? Easily.
Yes, sir.
So that's why our two flags, which is carry flag and overflow flag, will not be activated, because the result we are storing into the AL register, the lower part, it is 250, and it is enough for AL register to store that number. We don't need any bit from here. That's why the the two status flag, that carry and overflow, that means we don't have any carry, we don't have any overflow. All right, so these two flags are deactivated, not activated, on or clear. Fine. Look, so that's why if it is not needed, if AH is not needed, what it will be? It will be all zero. If you don't need the AH, because the AL is much more enough, so the AH will be all zero. That's why they have written that AH register will be all zero. Fine. Okay, let's have another example. Look at this example, similar type of example. Instead of 25, now we are using 26, the decimal value. What is the result now? If you multiply 260, right? 260.
255.
No. 10 multiplied by 26.
260. 260.
260, yes, correct. So if you multiply this number, that means at 10 multiplied by 26, that is 260. Do you think it is possible to store into AL register?
No. No, sir.
No, right? Because we can store maximum 255. So what will happen then? What will happen then? Our two status flag, carry and overflow, will be activated, or set, which will be activated, and it is just give you the status that yes, AL, the result cannot be stored entirely in AL, because the result is 260, and we need some of the bit from the higher order of AH register. That means now AH register are not all 0000. Okay, some of the bit is required from AH register, because this is 260 and you require more than 8 bit to store this 260 value. That's why whenever the flag is on, that you have a overflow and you have a carry bit, that means the processor will understand, yes, whatever the data is inside the AH register, it is part of the value of AL register. Do you understand? All right, so previously it was less than 255. That's why our all AH is 000 and our flag are deactivated, because we don't need any bit from here. But if the value is more than 255, then the two flags, carry flag and overflow flag, are activated, and the processor will understand then, yes, whatever the value is inside this AH register higher part, it's actually the part of the value of AL register, because the number is overflowed from and it has a carry bit from AL register. That's why we have these two register. So that's how we can do, and it is the same rule for AX register and DX for 16-bit, and it is also true for this and that. We are just having example of 8-bit register, but this process or these steps or this explanation is similar for both of them, like 16-bit and also 32-bit. Fine. For unsigned multiplication, we are going to use different instruction, which is in this case IMUL. In short, I mean the explanation is integer multiplication. All right, so it is IMUL, integer multiplication. Whenever you are trying to multiply any unsigned number, this is the instruction.
Unsigned or signed?
Sure, signed. Whenever you try to multiply the signed numbers, we are going to use this. In this case, we don't consider about the sign. That's why the instruction is just MUL. But if you want to multiply to signed number, then you have to write this IMUL. Okay. All right. Let's see how. What is the difference? First difference is how we can represent a negative number. We already know that how to convert it into the negative number, right? Okay, so we have to make it either 8-bit, 16-bit, and 32-bit, and then takes the 2's complement, and the result of 2's complement is your negative number of that positive number. So let's consider this is a one number which is a minus 66. We can convert this 8-bit minus 66 into 16-bit minus 66 like this way, just adding 1111 because this is a negative number. All 8 bits are representing the sign bit of this number if you convert it. Let me tell you again, this is the equivalent of minus 66. That is the equivalent of minus 66 in 8-bit. If you want to convert this minus 66 into 16-bit minus 66, what you need to do is just add another 81 because it's a negative number. That's why all are 1111. Fine. Similar way, very similar way, this is the equivalent of plus 66. Okay, plus 66. This is the positive 66 in 8-bit. If you want to convert this one into the 16-bit plus 66, that is the plus 66 with all 0000 because this is a positive number. Fine, we understand these two difference. This is negative number, we converted negative number from 8 to 16-bit, and now this is positive number 8 to 16-bit. All right, this is negative 66, that is positive 66. For negative, we add all 1 to make it 16-bit. For positive 66, we made all 0 to make it 16-bit positive 66 number. Fine. Okay, so let's multiply two. By the way, the I multiplication is very similar to the normal multiplication. That means we are going to use the same way, same thing. In signed multiplication, the process are exactly same, but just the difference is the number, the representative of the number. But the process and the storage and the technique is all same, everything same. Okay, so let's see how we can do a multiplication. So look at it here. We are moving, by the way, this is hexadecimal number. So we are moving this hexadecimal number into the DL, which is 8-bit long, another hexadecimal number into the AL register, which is another 8-bit long, and then we write IMUL. That means when you write IMUL, that means we consider whatever the value it has in AL and DL register, the microprocessor will think that yes, this is a signed number. Okay, this is a signed number. They consider it as a signed number whenever you write IMUL. Fine. So this number is actually equivalent to -1, and this number is equivalent to plus 66 into the AL register. So whenever you multiply this, it should be -66, right? -66, and the result will be this. We know that this is -66. This is -66. Okay. Fine. All right. But the okay. All right. So if you remember, whenever we multiply these two numbers, what actually happened? our carry flag and overflow flag are activated or not activated? Here,
Not activated.
because what is the reason? Because the number we are saving here, it is less than 255, right? That means we don't. That means we don't need any number from here, this register. Same way we are going to have in here also. Whenever we multiply these two number, the answer. What is the answer is? Minus 1 multiplied by 66 is minus 66, right? Minus 66, and minus 66 can be represented in 8-bit, right? This is minus 66. So we can easily store into our AL register. We don't need any bit from this register. So whenever we store into the AH register, all of them will be 1, because whenever we make it, look at the result, is actually this is the original minus 66, and all of them are 1 because it is a negative number, and because we need to fill up this register also. Previously we fill up by 000, but now it is a negative number, so, and it's a signed number, that's why we fill up it all 1111, and the result is minus 66. It is actually stored here, and that's why our two flag, what is the two flag? Overflow and what is the other one? Carry flag. Carry flag and carry flag and overflow flag will not be activated in this case. Well, in this case, because the answer is minus 66, and we can represent minus 66 in 8-bit, like this. Okay, do you understand? All right. Okay, so the result is minus 66, no problem. Let us have another example. Let's say we are multiplying minus 1 and minus 66. What will be happen? What will be the result? Plus 66, right? Plus 66. So do you think that we can store plus 66 into 8-bit register here?
Yes, sir.
We can store it, right? Plus 66 by 8-bit. So we can do that. So do you think that we need to activate the flag, two flags, status flag?
No, sir. No, sir.
No, why not? Because yes, because the example we are showing here, the result is plus 66, and we can store the plus 66 easily by 8-bit like this. We don't need any extra bit from the AH register, right? Fine. So that's why, and the result is plus 66. That's why all of them are 0. That means these are the AH register into the AH register, and these are into the AL register. So no problem. But think about this one. This is the third example, where we are multiplying 25 with minus 10. What will be the result? Minus 250, right? Minus 250. And minus 250, it is not possible to store minus 250 into 8-bit register. Don't confuse with the positive one, please. Positive 250 is possible to store here into the AL register, but this is negative 250. So for the negative 250, it is not possible to store into 8-bit register. That's why, what do you think? Our flag should be activated, right?
Yes, sir. Carry and overflow.
Yes, our flags, that means the carry flag and overflow flag, should be activated in this case, because the result is minus 255, and it is not possible to store this minus 250 into our AL register. We required some of the bit to store this minus 250, and we need to have some bit from AH register. That's why our two flags are on or activated, and that's why the processor will understand that, okay, some of the bit from AH register are not all the signed bits. Some of them are part of this. Okay,